All right, so guys, section 9.5, the binomial theorem. Like I just got through saying, pretty confident that you're going to recognize a lot of this stuff. One of the biggest challenges that we have ahead of us today is going to be the vocabulary, the terminology. There's going to be a lot of things that sound more complicated than what they really are. Okay, hopefully by now, late November, we come to expect that each day. That all right, how are we going to make this stuff sound worse than what it really is? That just seems to that's math now. I'm sorry if that's disappointing, but that's kind of where we're at. Is that again, we have some fancy terminology, we have some complicated or intimidating sounding ways of saying things, which again, it can sound all fancy, but at the end of the day, do we understand the math that we're actually doing? That's the goal. All right, so stay with me on the vocabulary terms. Again, I would highlight some things in your notes, circle them, star them, whatever it is that your system would be. But we're going to be talking about and using a lot of terms that are probably going to sound vaguely familiar from previous math classes. But again, some of the application is going to be a little bit more intense, or I don't even know if intense, but more intentional is probably the best word we could use. All right, so the goals that we have here today, 3 of them: students to be able to use binomial theorem to calculate binomial coefficients. Number 2, students to be able to use Pascal's triangle to calculate binomial coefficients. And then number 3, students to be able to use binomial coefficients to write binomial expansion. So again, really sort of ripping the Band-Aid off there by just reading through that stuff quickly. Binomial theorem, binomial coefficients, Pascal's triangle. Again, we're using those terms, pretty interchangeably. From goal to goal. Like I said, hopefully when we hear those terms, they sound vaguely familiar. If not, maybe obviously best case scenario is you hear me say one of these things and you know exactly what I'm talking about. That'd be outstanding. Not quite the expectation, but again, hopefully we're able to zero in and understand. But obviously, the more we understand the terminology, the easier the math is going to be. All right. So the first thing that we want to do, and I actually want to adjust this ever so slightly. I'm fully aware that you can see what's behind the shade that I'm creating here, but we want to go ahead and look at this setup. All right, so we keep talking about this binomial expansion. That's kind of the big deal for today. So as you can see, the target that I wrote up here on the board, we want to be able to use binomial theorem for binomial expansion and determining binomial coefficients. So this is the setup of our first 6 lines of binomial expansion. Now, hopefully, we all are fully aware, but I think I've already said the word binomial 15 times. Do we fully, completely understand what a binomial is? Somebody want to give it a shot? Somebody feel like we know what a binomial is? Ben, what have you got?
There's 2 terms separated by addition sign and subtraction sign. Addition and subtraction.
Yeah, there we go. Perfectly said. Again, it's when we have 2 terms separated by addition or subtraction. And that's pretty much it. So here, x plus y, that is our binomial. X plus 5, would that be a binomial? Sure. 7x plus 5, is that a binomial? 7x plus 5y, is that a binomial? 7x plus 5y minus 1, is that a binomial? No, what's that? It's a trinomial. Okay. So we're talking about binomial expansion. So again, 2 terms. We're adding or subtracting 2 terms. We're going to, for the most part, think of it in terms of addition. If it were a subtraction problem, we're just thinking that we're adding the opposite. Okay? But let's not overcomplicate things. Binomial means that we have 2 terms that you're adding or subtracting together. So in an attempt to be as generic as possible, we're going to go ahead and write out the expansion for x plus y. X plus y is, again, the most generic binomial that we could possibly think of. X could be anything, y could be anything for the most part. Okay. If we have a binomial, just like if you had an integer or any monomials meaning single term, anything to the 0 power is going to be 1. So that doesn't change if we're talking about binomials. Okay. Similarly, thinking about exponents here, anything to the 1st power is going to stay the same. It's going to remain. So for that reason, x plus y to the 1st remains x plus y. Then we have x plus y quantity squared. We know that we're not just going to distribute the exponent through. Again, there's more to it than that. So if we have x plus y squared, we would probably think, all right, we're going to rewrite that and FOIL it out. My question to you, again, I am not concerned with are we seeing the pattern until maybe when the exponent is 3 and above, okay? I would imagine that some of you had Algebra 2 teachers that made you do a lot of the expansion by hand. It wouldn't be the worst thing in the world by any stretch. Again, if you had x plus y quantity cubed, I'm sure that you could do x plus y to get this, and then multiply that times x plus y using distribution. It's totally, completely doable. Plus, there are going to be some shortcuts and tips and tricks along the way and things like that. What we're saying, though, is that, in math, you get it, you know it, we love patterns. It's all about patterns. If we can recognize and understand some patterns, we're going to use that to our advantage as much as we can. So here we go with another pattern. Like I said, we stopped at the 6th line when the exponent was 5, but please don't assume that the pattern actually stops. Again, we stopped here because we're kind of out of space. Again, this pattern is going to go to infinity for that matter. But a few things that we want you to, excuse me, to notice again. So some of the stuff that we have behind the shade here that you can see. First thing we want to notice is that in each expression there are n plus 1 terms. Now let's not overcomplicate things. N just represents the exponent. So all day long throughout section 9.5, we're going to see a lot of formulas and things like that. N always represents your exponent. So in this first line, we know that n is 0. That second line, we have n is 1. Here, n is 2. Here, n is 3. Here, n is 4. And finally, n is 5. Again, just looking at the exponents. So first things first, do we understand that n is just the exponent? Can I get like a head nod or thumbs up or something? Okay, we get that. Seems like a simple concept, but boy, is that crucial. If we jump into the middle of tonight's assignment and we've somehow forgotten what n represents, we're in trouble. Okay, things are not going to just accidentally go well. Okay, we have to know that n represents that exponent. Okay, so if we're saying that in the expression there are n plus 1 terms, let's take a look at the biggest one. In this particular case, the last one, the 6th row, we're saying that n is 5. So that means that we should have 5 plus 1, or 6 terms. We have 1, 2, 3, 4, 5, 6 terms. Seems to check out. Okay? If we looked at this third line here, where n is equal to 2, 2 plus 1, we should have 3 terms, and we do. Okay? So that's how this is going to work. One of the reasons why we want to pull this up is I recently saw on an ACT practice test, they had it written out this way, x plus y to the 99th. How many terms does this have? That was the question on the ACT exam. Now, could we expand the entire thing out? We're going to talk about how to do that today. You could. That would take you probably the full 60 minutes of your ACT exam. But if the question is how many terms do we have, this is actually a relatively simple question. What would you say? It's going to have 100 terms because 99 is n. 99 plus 1 is 100, right? Okay. So, again, that's the first pattern that we want to recognize and understand. Okay, the second thing that we want to see and understand is that the powers of x decrease by 1, the powers of y increase by 1. Now, please, again, realize that we're using x and y just very generically, but x represents the first term, y represents the second term. So we're going to go back to referring to these as x and y, but as we look at any of these, again, let's just focus on the biggest one. Here we have x to the 5th, x to the 4th, x to the 3rd, x to the 2nd, x to the 1st, and technically we even add x to the 0 over there, don't we? Similarly, we have y to the 0, y to the 1st, 2nd, 3rd, 4th, and 5th. So simultaneously, as the x's are decreasing in terms of power, the y's are increasing in terms of power. Okay? Hopefully, again, we're not stating anything that you didn't notice on your own or that you haven't seen in the past. But in an effort to build these as we go, this is pretty crucial that we're understanding. Okay, the third thing that we want to notice is that the sum of the powers in each term is n. So again, we keep using this last line as well. If we look at each individual term and we add the exponents together, 5 plus nothing is 5. Here we have the x to the 4th, y to the 1st. So again, looking at my exponents, 4 plus 1 is 5. Here the exponents 3 and 2, 3 plus 2 is 5. Here they're 2 and 3, 2 plus 3 is 5. Here we have 1 and 4, 1 plus 4 is 5, and then 5 plus nothing is still 5. Okay? And if you look back through the other 5 rows, they're going to be the exact same. All that we have to do is look at any particular term, and the exponents should sum to n. Last thing we want to point out here and notice is that the coefficients, they're going to increase and then decrease in a symmetric pattern. So now we're looking at the coefficients. As we can see, our coefficients are 1, 5, 10, and then the decreasing 10, 5, 1. It's going to work that way every time. It's going to go up and then back down in that stair-step pattern. All right. Any questions about this listing that we see so far? Okay. All right. So this leads us to what we call the binomial theorem. So the binomial theorem, we say that in the expansion of x plus y to the nth power, again, this is technically the binomial theorem. The piece that we're going to need to know is this guy right there. Okay? That's kind of that explicit definition, that generic pathway in order to get there. Okay? So we're going to say that if we've got x plus y to the nth power, that the coefficient of x to the n minus r, y to the r, is going to be given by this. Okay, it's a combination. We're going to talk about that a little bit deeper in the next slides. But again, we have two different ways that we could write out a combination. The more common for us would be NCR. Write it out this way. That's the way it looks in your calculators when you type it in. We could also write it out this way. Okay. So what we mean by that, Kennedy, give me a number, anything you want, please. 4. If we had 4C, I don't know. Jason, give me a number, but it has to be less than 4. 3. All right. So if we had 4C3, this is the way. And again, maybe it's just me personally, but I feel like this is the more common way of writing it. Okay. Please understand that another alternative way of writing it is 4C3. We could write it that way. Okay. Now, in a statistics class, what I'm told, again, I'm not taught a stats class. I don't necessarily remember it as a stats student, but I've been told, oh yeah, we write combinations that way a lot in statistics. Okay, so if you find yourself next year in AP Stats, or if you're a senior now and you're freshman year in a stats class, you may see it written this way. The way that you type it in on your calculator, once again, it's going to look a lot more like it. They are equivalent. They mean the exact same thing. All right. So this is that binomial theorem. This is what we're going to need to know. Usually pretty much whenever we show a formula or something of that nature, a lot of times people want to know, well, like, are you going to give us this? Probably not. This is one that, like I said, our game plan is that we're going to use this enough over the next couple of days to where we'll have it down. Okay, we'll have this thing down. It's really not as complex as it may look initially, but again, right now, it being relatively new, again, there's a good chance that you're remembering it from last year, but for the most part, it looks like we just have a lot of different variables up there, but again, you're going to, again, find that there's a distinct pattern. All right, so again, this NCR times, again, the kind of the rule there, x to the n minus r, y to the r. Remember, x just represents your first term, y represents your second term. So again, once we actually start doing some of these actual problems, hopefully it makes a lot more sense. But again, we need to do a little bit more here on what the combination stuff is all about. So I added something in here. I would encourage you to absolutely write this down. Not that we plan on doing a whole bunch of these by hand, but if you find yourself doing these by hand, this is the way you're going to want to do it. Again, I'm fully aware that you have a button on your calculator that's going to do all this stuff for you. But what we could do essentially is we could recognize the NCR. It's really equal to NPR divided by R factorial. Okay. These are going to be combinations. Again, if you're using a calculator, again, graphic calculator, hit the math button. Scroll over to PRB, should be your third option down. PRB for probability, of course. If you're using a scientific calculator like this, again, you see, let's see, 1, 2, 3, 4 buttons above the 7. Or if you find the second button in the top left, go right one, down one. There's your PRB button, and then as you can see, the combinations are there for you. All right, so as we just got through saying, we have two options as far as how we get there. So 8 choose 2. Again, I'm sure that you could beat me with typing this into your calculator, but what this really means is 8p2 over 2 factorial. So if you have forgotten how permutations work, the first number 8, that tells us what factorial to use. So 8 times 7 times 6, 5, 4. But we're going to stop after 2 terms. So that's 8p2 divided by 2 factorial. It's going to look like this. 56 divided by 2 is how much?